just so you guys are aware, I think I told you this yesterday. I don't remember if I did or not. We are doing a lab tomorrow. Okay, so please, 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 what kind of shoes? Closed-toed. Jeans, if you want to. If you don't want to wear long pants, that's fine. I'm not a big stickler on that. If you want to wear like wind pants, like bring them in, just kind of slide them over your shorts, that's fine. If you want to. I'm not going to be like a stickler. If you want to bring them, that's fine. Ladies, make sure you bring something to put your hair back with. Make sure no jewelry, no jackets, anything like that. And if we have enough time at the end, we'll go through the instructions. You have one thing to do for homework. Very simple. Let me just go ahead and show it to you in case we don't get to it. I'm going to email this out. These are the instructions for the lab tomorrow. All I want you to do is read through the first page. I know it looks like a lot, but it's just step by step of what you have to do. So when you come in here, we can get rolling. We don't have to stop and wait. So everybody knows what's on the agenda. All I want you to do is just read it. Okay, that's all you have to do is read through it. And this is the back. It's just the data table, so it's where you fill stuff in. So please just read through that tonight. You can even read through it tomorrow when you get to school. Like if you're in a class you don't have anything to do, before you come in here, just please make sure you've at least read through it one time. Okay? All right. So going back to this, I'm going to set the groups tomorrow. Yeah, I'll set those groups. Okay? So where we left off yesterday that we didn't get to see on this video was this particular sheet right here. So what we were doing is we talked about 4 different substances that were 10 grams each, and we left them in sunlight for 60 minutes, and we wanted to know how fast they warmed up. So what we did is we took all these data points and we plotted them on our graph. And again, I apologize about the graph. I know it was really hard because the lines weren't there on your paper. Sometimes the copy machine doesn't work that great. All right, so looking at all of these, so let's do this to make it a little bit easier. All right, we said that the diamond was a metal, so I would come in here and write this. That way it's easier for you to recognize it, okay? The triangle was sand. The blue circle was air. And then the purple square was water. All right, and then those of you that got finished plotting the points, what I asked you to do was the 2 questions to the right of the graph. It says, order the substances based on the time required to heat them from slowest to fastest. Okay, so what substance heated up the slowest? Water. Very good. So I'm just going to write W for water. What was the second slowest? Air. Fantastic. The next, sand and metal. So water, air, sand, and metal. Again, I just put the first letter for each one of them. How can you tell based on the graph? And give me a mathematical expression. What could you say about water? How do you know it heated the slowest? Say it again. Slope. What do you notice about the slope of water? It's the shallowest, right? It's the lowest slope. Does that make sense? So that's another way to think about it. So really, what was the change in temperature for water? How much did it go up after an hour? Only 5 degrees, okay? How much did metal go up after an hour? 40. So 5 degrees versus 40 degrees in the same amount of time in the same direct sunlight. Is that a major difference in temperature? Yes, okay? All right, number 2. Which do you think will cool the fastest? All right, let me ask, how many of you say air? How many of you say water? How many of you say sand? How many of you say metal? Very good. It is metal. Okay. So it's this kind of the opposite concept. The faster it heats up, the faster it does what? It cools down. Okay. So it would be metal because the amount of energy, because if it absorbs energy really fast, what does it do with the energy also really fast? It releases it really fast. So it's kind of the opposite concept. So if it takes a really long time to heat up, it should take a really long time to cool down, right? So if you boil water, can you just automatically stick your hand in it? No, that's a really bad idea, okay? If you take cookies and you put them on aluminum foil, you put them in the oven, cook them for 20 minutes on 350 degrees, you pull them out, and it's on aluminum foil. How long is it before you can grab that aluminum foil with your bare hands? It's almost instant. Within a few minutes, you can take that whole thing, ball it up, throw it away, okay? Really, you can. Okay? Any of y'all have like a toaster oven? You know what I'm saying? Like if you put it on tinfoil, you can pull it almost immediately and grab the tinfoil and set it down on something. Now, I wouldn't grab where the food is, but you can grab where just the edges of the aluminum foil. So it loses its heat really quickly as well. All right. Any questions on the specific graph? Okay. All right. Number 3. When you boil water in a pot on a stove, I don't know how else you would do it, which heats faster, the metal or the water? Very good. Metal. How do you know? And this is where we're going to get into our specifics. Very good. We talked about this yesterday. What does CP stand for? Specific heat. It has the lowest specific heat. On that table in your notes yesterday, do you remember what had the highest value? Which kind of water? Liquid water. Did you say? Never mind. Liquid water. Number 4. Why do you think different substances heat up and cool down at different rates? Different states. I like that. Anything else? What do you mean by thickness? Give me a better word than thickness. The density. Do you think the density has anything to do with it? There's one more thing. All right, so there's another thing. So bonds. So far, Grayson, what'd you say? The state of matter. Mason, you said density. James, you said bonds. And there's one more thing that I'm looking for. Jackson? What gives things its properties? Very good. The chemical makeup. That was the thing I was looking for. The chemical makeup. So what it's made out of. Okay. So brass and steel. Can you find either one of those on the periodic table? You can? No. What are those mixture of metals called? Alloys. Okay. So they are made up of different elements. So if you took brass, steel, iron, and lead, they're all metals, but do they have the same chemical makeup? So they're going to have all these different things. So these are some ways and some reasons that things heat up at different rates. Now, it says specific heat capacity, the amount of energy needed to raise the temperature of 1 gram of anything by 1 degree. So based on the definition above, which of the 4 substances do you think has the highest specific heat capacity, which means it needs the most amount of energy? Water, very good. Okay? And then which do you think has the lowest? Metals. All right, number 6, I'm going to kind of need your eyes for just a second because I want you to kind of do it a specific way. All right, number 6 says, here are the heat capacities of the 4 substances, and it lists 4 numbers in the units. Match and then label each substance with its specific heat capacity on the graph. Again, this is just me being an analyzing person. Do me a favor. We're going to add another row to this thing, to this graph right here, or this table, if you will, and we're going to label it specific heat. Now, you can't see it because I had to scroll up on the board, but you guys can still see it on your paper. Yeah, CP's fine. You're starting to think like me. It's nice to have symbols, isn't it? Instead of writing change in enthalpy, delta H is really nice. Okay? Here's what I want you to do. Those 4 numbers, again, you can see them on your thing. Put those 4 numbers in the column where you think they belong. Now, use the previous question to kind of help you out. But see if you can figure out where those 4 numbers belong. Those 4 numbers are in question 6. Plug them in under what substance the number is associated with. And use the previous question to kind of help you out. The more energy required to heat it up. Which one has the highest value? Water. You already established that. What was that number? 4.18. If you want to put the units in, that's fine. I'm just going to be lazy for this one and not do it, but the units are important. Now, I'm kind of begging. I really am begging. Please memorize that one number. Water specific heat is 4.18. You're going to use that number a lot. Okay? Now, what was the lowest substance? What's the lowest specific heat? Metal. And what was that number out of that list? 0.60. Now, this is where you got to figure out. We know those two. Those were kind of easy. You have to figure out which one was the next. Let's go ahead and do the next lowest. So what was right above metal? How many of you vote sand? How many vote air? Okay, it is sand. Very good. And what's the number, 0.7 or 0.8? 0.80. And then air is what? 1.00. Okay. So again, the more energy required to heat up means the slower it heats over time because it requires so much energy, especially if it's the same amount of energy. All right. So let's go down and look at number 7. If something has a high specific heat of capacity, will it take a lot of heat or a little heat to change its temperature? A lot of heat. Let's do this one and I'll come back to it, okay? It'll take a lot of heat. Can someone tell me why? Okay. That's the heat capacity. It's its ability to hold in heat and not allow it to change it, okay? So careful, use the definition, your graph, and the data from number 6. Again, I'm not necessarily really concerned with the explanation other than the fact that it just requires a lot of energy to heat up. All right, James, your question. Yeah. Yes. Basically, is that our standard? I would assume that is true. I don't know that for a guaranteed fact, but I would assume that is true, yes. The density and all that stuff, yes. Yeah. I would be willing to bet that's the case, but I don't have any concrete evidence of that, no. Okay? All right, finally, number 8. Assuming they both start at the same temperature, which will heat up faster? A swimming pool or a bathtub, Caleb? Why? Okay. What variable could you use to say there's less of? The density is the same no matter what. If it's a bathtub or a swimming pool, the density is the same. Now, it's interesting that I hear both answers. I hear volume. But in our formula that we've been working with, this formula, matter of fact, it's on the back of yours. Just kind of look right here. That formula right there. Which variable are we going to be dealing with in this? The mass. Now, if you know the volume of water, do you also know the mass of water? Yes. 1 milliliter is how much? 1 gram. This is the important part. If you have 1 liter of water, how many grams is that? 1,000. Because how many milliliters are in a liter? 1,000. Milli means 1,000. Okay. So if you've got 1,000 milliliters, you've got 1,000 grams. So what happens if you have 10 liters? 10,000 grams. Okay. So there's more of a mass to heat up. So there's more water. In essence, you would have to heat up. So the bathtub will heat up a little bit faster, even though they will heat up at the same rate. So that's kind of what you could put. You can put a bathtub because there's more mass in a swimming pool. All right, any questions on that? All right, so here's where the fun starts. Let's do the back. If you'll flip over. Don't laugh at me. Now, I want to see how much you remember. If you have that packet of notes available, you are more than welcome to use it, but I would rather see if you can figure out on your own. So number 1, for Q equals MC. Now, real quick, we talked about it yesterday. What do we do to that C? Add a little P behind it. Does anyone remember why I said the P? Very good. There's another C that we'll talk about later that represent, and I don't want you to get them confused. Anybody remember what the C represents? Very good. Speed of light. Fantastic. Okay. So here's what I want you to do. I want you to write each variable, identify what it means, and its unit. I want to see if you remember that. Okay. If you don't know one of them, just skip it. But do the ones that you do know. I'm telling you, the unit on specific heat's the one that's going to get some of you. Okay, so let's start with the first one. Q. What does Q stand for or represent? Very good. Now, some of you said energy. Did anyone write anything other than energy? Not quite. How about heat? Did anybody write heat transfer? Very good. Either one works. Okay. What is the unit for it? Joules. Very good. Capital J. All right. Now, I cheated and I gave you M. M stands for what? Duh. And what's its unit? Grams. Now, I'm going to skip the hard one and come back to it in a second. Triangle T. What is triangle T? Very good. Change in temp. Now, here's an important question. Which unit? Very good. What's that key word? Or Kelvin. And we're going to see that down here in some of these examples. And I'm going to be honest, most of them are in Celsius, but do not freak out if you see Kelvin. Okay, it's okay. Yes, sir. All right, that's a good question. I always get this question because I always write it like this and people look at it. And I don't know why it's this way. I'm just telling you kind of a fact. That it is degree Celsius and it's just Kelvin. Now, why it's not degree Kelvin, I have no idea. I've read that somewhere and I know that that's a fact. So I put the little degree sign on Celsius but never on Kelvin because of that. I don't care. Either it's 6 1/2 a dozen, the other's the same thing to me. We know what we're talking about. All right, and the last one. CP. What does it stand for? Specific heat. Did I spell that right? Here's the deal. The unit is important. So if you have some room somewhere at the bottom or at the top of this, redraw all this for me. Because as we go through this, the back of this, the math, this is going to help you guys out. So on the test on Monday, the two problems, it may behoove you to draw that. Behoove. Be in your best interest. That's what we're fixing to do right now. Yes, sir. No. I'm pushing those back off. All right. So we know the three variables. What is the variable for Q? J. Okay. What's the variable for M? G. And then does it matter which temperature? Nope. Let's just throw in degree C. If we did that mathematically, would any of those variables cancel? So that is the unit. Okay? That is the unit. I'm telling you now, after years and years and years of doing this, this is one of the most missed units that we do all year long. I don't know why. People just always forget what it is. Yes, sir. That is it. That's it. Okay? So when you start working with this, I'm stressing the point of write it down so it becomes a part of your ingrained muscle memory. Okay, and I'm not rude about it. I'm just telling you. Over years, I've noticed that this is a point of issue for a lot of students as they forget that thing. All right, so let's look at number 2. Heat is not the same as temperature, yet they are related. How are they different? Can anyone remember the definition of temperature for me? Anybody remember temperature? It's the average, AVG. Does anyone know what KE stands for? Did you say killing beavers? Kinetic energy, very good. What is kinetic energy? Energy that is in motion. It's moving things. Okay, do particles move? all the time. Okay, that's how we have life. So it's the average kinetic energy of the particles. Yes, sir, please do. That is temperature. It's the average kinetic energy of the particles. Another abbreviation that's really nice for us to have, KE. What would potential energy be? Amazing. All right, so heat. Anybody remember heat? Cody, you said you remembered it. It's a transfer of energy, and this is the important part, due to delta T. A transfer of energy due to delta T. I'm forewarning you, on your test on Monday, one of those definitions is a test question. I won't tell you which one, but one of them is. It says, what is the definition of heat? Or what is the definition of temperature? Okay, or it could be the backwards. It could give you the definition, and you got to know what word it applies to. One of those is on the test. Now, so let me give you another example of heat. If I take water and I put it in a pot and put it on a stove, how do I heat the water? What has to happen, like physically? Kind of tell me what's going on. Okay. The eye get hot first, right? What do I need for the eye to get hot? Flip the switch. Okay, but when you flip the switch, what happens? Electricity. So it's electrical energy that heats that eye. Then what happens to the energy from the eye to the pot? It's transferred. Why? What is delta T? Is there a difference in temperature of the eye and the pot? So the energy transfers from the hot to the cold or cold to the hot? Hot to the cold. Well then, just because the energy transfers to the pot, does that automatically make the water warm? Then what has to happen? Transfers to pot to the water. Now, it would be a lot more efficient if we could put the water on the stove, like just it hold itself there, but that doesn't happen. Okay, physics doesn't work that way. So that's why we need a transfer of energy. Because if we didn't have a transfer of energy, nothing would ever heat up. And so that's important to understand the difference between the heat and the temperature, because the water heats up because of that transfer of energy. Okay? Well, then how do you know if it'll burn you or not? You put your hand in it, and the temperature, the average particles. So if it's really hot, are the particles moving really fast? That's what burns you. Okay? Any questions on that? The harder they hit you, the worse it feels. Yes, sir. Specific heat? No. All right, so here's the deal. So particles have two forms of energy, vibrational and rotational. That's getting really, really deep. So atoms either shake, like they're vibrating. They're not twerking, they're vibrating. Okay? Or they spin really fast. Okay? Well, think about something that's spinning, and it's connected to something else that's spinning. What is created between those two things? What kind of energy? Friction. Well, does friction heat stuff up? That's what allows things to get warm. So the more energy you put in it, what do? They vibrate faster or they spin faster. That's the same. They do the same thing. They can either shake or they can spin. Well, the more energy you put in, the faster they do those things, so the more friction they cause, so the more heat they have, so the more heat they give off. Yes, gold takes less energy to make them shake faster. Yes. Yes. How many of you are like TV and tech nerds? You know what an HDMI cable is? Okay. Of course, you got to hook up your Xbox, right? So think about it. If you go to Best Buy and want to buy an HDMI cable, the most expensive ones have a gold tip on them. Look it up, I promise. They're like $30, $40 more because it has a gold tip. Why? I mean, you're not paying for the gold. Why is the gold more expensive in terms of efficiency? More conductive. So the image or the energy can transfer faster. It's a better refresh rate. It's essentially. So if you could afford it, instead of using copper in your house for wires, you could use gold. If you could afford it. Platinum is in the same ballpark. It's less than gold, but it's in the same ballpark. It's more conductive. Yes, you're exactly right on that. Yes. Yes. Yeah, friction from the atmospheric air. Yep. So a shooting star is essentially just a meteor burning up in the atmosphere. Okay. All right. So let's look at number 1. So we have this formula right here above it, and then we need to do 2 things. We need to calculate Q, and then we need to determine if it's endothermic or exothermic. Real quick, when you calculate these answers, if it's positive, is it endothermic or exothermic? All right, so put a positive above endo. If it's exothermic, what sign is it? Negative, very good. And I'm forewarning you, reading these questions is very critical, and you'll see that in the next few minutes. So number 1, gold has a specific heat of that value. How many joules of heat energy are required to raise the temperature of 15 grams of gold from 22 degrees Celsius to 85 degrees Celsius? So what's the question? Okay, joules of heat energy. Now, what variable would that make us be solving for? Q. So Q is equal to M Cp delta T. All right, well, let's start out with what we know. What's the mass of the piece of gold? 15 grams. All right. The next easy one. What is the specific heat of gold? And I'm begging you now, don't be lazy. Please, please, please write that unit in. Again, get in a habit of writing it in. I want to ask this as a follow-up question. If this word right here was removed, find that orange line that I just drew. If those words were removed, the word specific heat, how could you still know that that number was the specific heat? The unit. Very good. Okay? And then the last thing, delta T. I've got a problem. I've got 2 temperature units. Which one is it? It's a trick question. That was what I was fixing to get into. Here's what I need you to understand. It is all well and great and fantastic that you guys know what delta T means. Please write this down. When you say change in, it's changing. But how do you calculate a change? Tomorrow during the lab, this is going to be crucial for your understanding of how to calculate Q. So delta doesn't mean change in. It does in terms of a definition, but what does it mean mathematically? Final minus initial. So how you read this question is very crucial to doing the math right. So this is a from and to question. So what number was the final number? What did we end with? 85. You've already calculated it. So you have 2 ways of doing it. I don't care which way you do it. Let me show you. You can either write it like this. 85 degrees C minus 22 degrees C. Or you can do what Cody did. Cody, what did you do? Very good. And how did you get that number? I don't care which way you do it. You get to have that leeway, as long as you plug it in and get the right answer on the back end. If you had done 22 minus 85, would you have the right answer? No, you would not. It would be the right value, wrong sign. Okay, and that's important to us. So, as far as a sign on this thing, is it positive or negative? A positive times a positive times a positive is a... Everyone every year always asks, do I have to do that? No, you don't have to. But let me tell you why I do it, especially when I'm calculating Q. The follow-up question is it endothermic or exothermic? That positive sign is a visual representation that tells you, I know exactly what it is. It helps you understand it and just visualize it without having to think about it. Now, what is this answer in the calculator? All right, we'll write that. But before I finish this off, let's throw this at you. How many significant figures are supposed to be in your answer? 2 of them. How can we round this to 2 significant figures? Very good. Positive 120. You can do all that beautiful work, and if you leave it like this, did you earn full credit? What did you miss if it's like this? The unit. 2 things. Number 1, what did you solve for? Well, it tells you right smack dab in the question. But if you look at your unit cancellation, do grams cancel and do Celsius cancel, leaving you with joules. Does that make sense? Okay. Now, final follow-up, endo or exo? Endo, very good. And how do you know? Because it's positive. Positive 120 joules. Yes, ma'am. Yes, ma'am. Get it close. Don't do what he did. Don't give me all that garbage. Okay, get it close. Here's how I'll do it. I always do it plus or minus 1. So if you had done 3, you would have been fine. If you had done 1, you would have been fine. Does that make sense? If you would have put 122 just for rounding, you'd have gotten credit for it. Okay. Now I want to do number 2 with you. I know we're running out of time, but I really need you to see it because the phrasing of this question is very important. An unknown substance with a mass of 100 grams, do me a favor, put a decimal point behind that 100. Why does that matter? Changes your significant figures, very good. And absorbs 1,000 joules of energy. Put a decimal point behind the 1,000 as well. Again, that changes your sig figs. I need to pause right here, and I need to make an important statement about this word right here. Draw a circle or underline or box that word. Absorbs. I've told you there's 2 ways energy is treated. What's the 2 ways? Absorbed or released. Is there a sign associated with those 2 words? What sign is associated with that word? A positive. You don't see it, but it's associated with it because of that word. Had this question been released 1,000 joules, a negative sign would not be there. Guess what you would have to know to do? You have to know that released makes it negative. Now, as soon as it says absorbs, what type of reaction are we working with? Endothermic. And again, the only way to know that is the fact this is energy absorbed or is energy released. So it's important that you make that connection. Okay? So it absorbs 1,000 joules while undergoing a temperature increase of 15 degrees Celsius. What is the specific heat of the substance? So what's the question? Specific heat, all right? So we have a formula. So the triangle at the top that you guys already drew, what is the formula for CP? Very good. Q over M times delta T. Yeah. All right. So Q, what is the value for Q? What 1,000? Positive 1,000. Again, why positive? You know it's absorbing and you know it's endothermic. All right, what's the mass of this unknown thing? 100 grams. And here's the best news. What's the temperature change? 15. Very good. So is it positive or negative 15? What word is right here? Increase. So it's positive 15 degrees Celsius. All right. How many significant figures are in that answer? 2. Very good. Anybody got an answer for me? 0.6 what? So 0.67. Now, congratulations, awesome, fantastic. You did it good, but you didn't do it right. What's missing? There you go. Again, that unit is going to be where some of you are going to mess up. I know we're running out of time, but I want you guys to try to do at least 3, and if you finish 3, go ahead and move on to 4. The more you do this, the better you're going to be at it. Okay, so again, we're going to do this tomorrow in the lab, so I need you to practice this as much as you can to get it right. Go ahead and start working on those. Again, think about temperature change, if it increases or decreases, and think about the words absorbed or released. Those are going to be very important.